Alrighty, so this is an extra video to go over the two amplifying circuits with one transistor in. So the type 1 and the type 2 amplifier circuits. So we'll start off with the circuit number 1. And as far as the DC is concerned, the circuit looks like this. We've got a resistor that's part of the biasing network, and another resistor that's part of the biasing network, and then we've got the base of a transistor and the emitter, and we've got a load resistor in the collector and an emitter resistor as well, which provides negative feedback for DC and stabilises the operating point of the amplifier. And we'll call this R1, and we'll call this R2, and we'll call this RE, and we'll call this RL. And we don't need to worry about any capacitors or anything like that, because we're only interested in the DC or quiescent conditions. And we can make some assumptions as well. The first thing we can say is that we'll assume HFE is much greater than 1, and or beta is much greater than 1. And what that will mean is that the ratio of the collector to base current will be very large, with the collector current being much bigger than the base current. And what we're hoping to be able to say is that the base current is an insignificant part of the emitter current. And if we do manage to say that, what we'll be able to do is say, well, there would be some base current here, but it's so small that I'm going to ignore it. So IB is equal to 0. Now, what that implies is that any current that flows through R1 and goes into the transistor is so small that it doesn't affect the current that goes into R2, because this current and the current in R2 have to add up to whatever the current in R1 is. So what we also need to do is make sure that the current flowing down here through R1 is so large compared to whatever the real base current is. Obviously it's not really 0. This has to be so big compared to that what does actually pass down here in the R2 is not much smaller than what flows through R1. And if that happens, that's another way of saying, well, look, IB is so small, it doesn't matter. So HFE is much greater than 1, so IB is insignificant for transistor operation, and the current in R1 is so big that whatever little IB there is doesn't make much difference to the overall value. And not much difference is sort of 5% or so. To actually solve the circuit, we'll do the equations first, and then we'll talk about a design afterwards. We have to use Kirchhoff's voltage and current laws, and for this circuit we only need the voltage law. So there are several loops available, voltage loops. So we can say that there'll be a voltage across R2, and I'm going to call it VB. You could, if you wanted to, call it VR2, that would be fine. But since this is the base electrode, and this is with respect to ground, obviously, I'm just going to call it VB. And the other thing we can say, well, we know what the voltage across this is the base to emitter junction. So this should be called VBE. And we know that's going to be about 0.7 volts. About. And we've got a voltage across the emitter resistor as well, and I'm going to call that VE because it's the voltage of the emitter with respect to ground, and it just so happens that's the voltage across the emitter resistor. And if it wasn't, I probably wouldn't have called it the emitter resistor, because it's nice and self-consistent. So that's one loop, because we know that VB has to add up to VBE plus VE, because that voltage and that voltage is the same as across there, so we've got a loop of currents and they all have to add up to nothing. That's Kirchhoff's voltage law. The other thing we can say is, well, we've got Vs here and we've got Vb. and there's a loop round there, so whatever's across R1 in terms of voltage, so we'll call it VR1. That wasn't very good. There we go. So VR1 plus VB must add up to VS, so I'll put a little VS there just in case, so now it's all in green. So what else can we say? Well, we're saying little h, big F, big E, or capital F, capital A, much, much greater than 1. Other thing we're saying, these are assumptions, is IE is essentially equal to IC because IB is essentially very nearly equal to 0, approximately equal to 0. Alright, so that's what we've got sort of verbally already. So now we need to write out some equations for these voltage loops that we've written down. And we'll start off with the VB and VE loop. So we'll have VB is equal to VE plus VBE, and we'll call that 1. And the other thing that we can say is that VB is also, so that was the summation of these two voltages to yield that one. But we also know that VB is VS multiplied by R2 over R1 plus R2. And that's the potential division of these two, of the potential division of this voltage across or between these two resistors. So we've now got two equations for VB, and we've also got I is equal to IC as well. We can start jiggling these, but something else we can say is that I have a voltage here to there, which is VC, and I could write an equation for VC in terms of VS, and to do that it's helpful to define a current that flows in RL called IC. We've already talked about IC up here. So we'll say that VC is equal to VS minus IC times RL. Now, IC times RL is actually just this voltage here, the voltage across the load resistor. So what I'm saying is that VC plus the voltage across RL adds up to VS. So I've done Kirchhoff's voltage law around that bit there, say using VC. And if you wanted to, you could say, oh well, VC is composed of VE and the VC of the transistor. But you don't want to do that, because the VC of the transistor is not something that ought to appear in your equations, and it's not something over which you have control either. So what we need to do now is to start substituting some values in to figure out what we'd like to see. Ultimately, we're heading towards an equation for VC. We'll start off by saying IC being equal to IE will be equal to VE upon RE, because I've got an IE here, Now, what I've set up here is IE equals IC because IB is 0. So for a regular transistor where IB is not 0, this current and that current sum up to give you the emitter current. So base current plus collector current is emitter current, but since the base current is 0, collector current must equal emitter current. If that's the case, we can also write that VE is equal to IC times RE, which is fine. So we'll have we'll call that one 3 if you like, and we'll call this one 4. So we'll do 4 into 1, and that will give us VB is equal to IC times RE plus 0.7, because we know that VB is going to be approximately 0.7. So that's 4 into 1, we'll call that one 5. And then we can say, well, we could sub 2 into 5 as well, and that will get rid of all the VBs. So we can do 2 into 5, and this will give us, so I'm just dropping this lot here in for VB. I'll have VS times R2 over R1 plus R2, that's an R, is equal to IC times RE plus 0.7. Fair enough. So then what? Well, if I just want IC, now I do want IC because what I'm hoping to do is drop this, which is 6, slightly rearranged into 3 to give me an answer for VC. But I've run out of board space, so I'm going to have to rub out the circuit in order to continue. So let's get rid of the circuit. So we're hoping to rearrange 6 and then sub into 3. So 6 rearrange, I'm going to subtract the 0.7 and then divide through by RE. So we'll end up with IC is equal to 1 upon RE, big square braces, VS times R2 over R1 plus R2 minus 0.7, close braces. Alright? Yeah, that's right. So we'll call this, it's not, I'm not going to call it 7 because all I've done is shuffle the terms in 6 about to make them a bit more useful to me. So in that case, the only thing I'm left to do now is say, so this is 6 as well, but slightly rearranged. 6 into 3 will give me an expression for VC. So I'll have VC is equal to VS minus 1 upon RE, so VS times R2 over R1 plus R2 minus 0.7 times RL. Yeah, that's okay. So it's just this lot has dropped in place of IC. So that gives you a value for VC, and I suppose if you wanted to, you could call that equation 7. And that's the analysis for that circuit. Now that doesn't actually tell you when. Okay, it tells you what VC will be. for any arbitrary set of resistor values and so forth, under the assumptions that we came up with in the beginning, which is fine. But it doesn't actually tell you how to design the circuit. It just tells you how to analyse one with algebra instead of numbers. So we'll do a quick example as well. I'm just going to rub this out now.